Good morning. My name is Purti. I am pursuing BTech first year in Triple department at IARE College. My course title is Engineering Physics. My presentation title is The Symmetry of Crystal Structure. Here I placed two images which gives you complete idea about my presentation. Introduction to crystal symmetry. Crystal symmetry pertains to the repetitive and uniform arrangement of atoms within a crystal. Understanding symmetry helps classify and analyze different crystal structures. It provides insight into the physical properties and behavior of materials. So, what is crystal structure? Crystal structure describes the ordered arrangement of atoms in a solid. It is characterized by a repeating pattern extending in three-dimensional space. The structure determines many of the materials' mechanical, optical, and electrical properties. Symmetry elements in crystals. Here I placed a picture which give you basic idea of symmetry. Symmetry is nothing but dividing a thing into two equal parts, or not only two, how many equal parts it can do. We call it as a line, those many lines of symmetry the thing has. Symmetry elements are geometric entities like points, lines, or planes about which symmetry operations are performed. Common symmetry elements include axes of rotation, mirror planes, and centers of inversion. These elements define the symmetry operations that leave the crystal unchanged. Symmetry operations defined. Symmetry operations are movements that map a crystal onto itself. Examples include rotations, reflections, inversions, and roto-inversions. These operations help identify the symmetry class of crystal. Point groups in crystals. Point groups describe the symmetry of crystal considering only symmetry operations that leave at least one point fixed. They classify crystals based on their rotational and reflexive symmetry elements. There are 32 crystallographic point groups recognized in three-dimensional space. Space groups overview. Space groups combine point group symmetries with translational symmetry elements. They provide a complete description of three-dimensional symmetry of a crystal. There are 230 unique space groups in crystallography. Lattice systems in crystals. Crystal lattices are categorized into 7 crystal systems based on cell geometry. These systems include cubic, tetragonal, orthorhombic, rhombohedral, monoclinic, triclinic, and hexagonal. Each system features distinct symmetry elements and lattice parameters. Coming to Bravais lattices. Bravais lattices are the distinct lattice types that classify crystal structures within each system. They represent the 14 possible lattice arrangements in 3D space. Here you can see in the picture there are 14 Bravais lattices in which cubic, tetragonal, hexagonal, orthorhombic, monoclinic, trigonal and triclinic are there. Structures, coming to the structures, cubic has primitive, body-centered and face-centered structure. Tetragonal has primitive and body-centered. Hexagonal has only primitive. Orthorhombic has primitive, body-centered, face-centered, and basis face-centered. Monoclinic has primitive and basis face-centered. Trigonal has only primitive structure, and also triclinic has only primitive structure. These lattices help in understanding fundamental symmetry and periodicity. The role of symmetry in material properties. Symmetry influences the physical properties such as optical activity, piezoelectricity, and conductivity. High symmetry crystals tend to have isotropic properties, while lower symmetry often results in anisotropy. Understanding symmetry helps predict how materials will respond under various conditions. Crystallographic axis and coordinates. Crystallographic axes define the primary directions within a crystal lattice. Coordinates are used to specify atomic positions relative to these axes. Symmetry operations often involve transformations along these axes. Symmetry in molecular crystals. Molecular crystals display symmetry based on the shape and arrangement of the constituent molecules. The symmetry influences molecular packing and crystallinity. Recognizing symmetry helps us in understanding molecular interactions and physical properties. Tools for analyzing crystal symmetry. X-ray diffraction is a primary technique used to determine symmetric elements in a crystal. Crystallographic software aids in identifying and visualizing symmetric operations. Symmetry analysis is essential in solving and refining crystal structures. Yes. Symmetry and crystal defects. Defects can locally break the symmetry in an otherwise perfect crystal. Understanding symmetry helps in analyzing defect types and their effects. Symmetry considerations are crucial in materials engineering and failure analysis. Symmetry and phase transitions. Changes in symmetry often accompany phase transitions in materials. Transitioning from high to low symmetry states can alter physical properties significantly. Studying these symmetry changes aids in understanding material behavior under different conditions. Symmetry and crystallographic notation. Standard notation uses symbols like Lloyd, Hermann-Morgan, and Schoenfeld to denote symmetry. These symbols succinctly describe the symmetry elements present in a crystal. Proper notation is vital for clear communication in crystallography. Importance of symmetry in crystallography. Let's see why is symmetry important in crystallography. Symmetry simplifies the analysis and classification of complex crystal structures. It helps reduce the complexity of diffraction data interpretation. Recognizing symmetry is fundamental in the discovery and design of new materials. Symmetry in mineralogy and gemology. Many minerals are classified based on their symmetry properties. Yes. Symmetry influences the optical properties and aesthetic appeal of gemstones. Understanding mineral symmetry aids in identification and valuation. Coming to applications of crystal symmetry in technology, there are many applications in this crystal symmetry in technology. Let's see few of them. Symmetry principles are applied in design, semiconductor device design and nanotechnology. They assist in tailoring material properties for specific applications. The symmetry considerations are essential in developing advanced functional materials. Coming to the future directions in crystal symmetry research. Here is a picture by which we can see the future is future crystal symmetry in technology. There are many people doing research on it. Advances in computational methods enable detailed symmetry analysis of complex structures. Discovering new symmetry groups can lead to novel material properties. Ongoing research explores symmetry role in emergent phenomena like topological insulators. So, conclusion is crystal symmetry underpins the fundamental understanding of crystal structures and properties. Recognizing symmetry elements and operations is key to classifying and analyzing materials. Ongoing research continues to unveil new insights impacting science and technology significantly. Thank you.